Hello there, students. Today we're going to learn about tensors and how they relate to vectors. A tensor is simply a mathematically defined object or construct used to group or classify other mathematical objects that behave or transform in similar ways. By their definition, tensors have two values that define them, their rank and dimension. Dimension is fairly intuitive and straightforward. If we're working in two dimensions, say with an x and y axis, a tensor in that space will also have two dimensions. If we move to higher dimensional space, tensors also match those dimensions. Rank, on the other hand, is less intuitive and is better defined in a linear algebra course. For our purposes in learning about vectors, we need to know that tensors have rank, and these loosely correspond to the number of directions it takes to represent the number of dimensions the tensor has. This will make more sense with some examples. In fact, you've already come across some tensors and you might not have even known it. The first type, and most basic type of tensor, is one with rank 0. We call these by a specific name, which is a scalar. Examples of rank 0 tensors or scalars would be mass, length, or time. It doesn't matter what dimension we're working in for scalars, they always have one value that defines them. 5 kilograms, for example, is written the same way in 2 or 3 dimensions. For example, mass m is equal to 5 kilograms. The next type of tensor is a rank 1 tensor, which we call vectors. Examples of rank 1 tensors or vectors would be velocity, acceleration, momentum, or force. The way we write vectors is dependent on the dimension we're working in. For example, a vector needs 2 values to define it in 2 dimensions, or 3 values in 3 dimensions. We can represent these values in a single column or row, though, which is why it is a rank 1 tensor. As we gain dimensions, and thus values we need to represent the tensor, or vector, the object only grows in one direction. See how, when we add the third dimension, the vector gets longer in a single direction? This is because it is a rank 1 tensor. As we add dimensions, and thus values in the tensor, it grows in the direction of the red arrow. The next tensor that we have a specific name for is a rank 2 tensor, which we call a matrix. These objects have both rows and columns, 2 arrays of values to define them, hence being rank 2. An example of a rank 2 tensor or matrix in physics would be the Maxwell stress tensor or inertia tensor. We won't talk much about matrices in this video or playlist since we're focusing on vectors, but you'll most likely see them in another course, so it might be nice to know that they are related. Tensors are sometimes indicated by the double arrow over a letter, as seen here in the example of the inertia tensor in 3 dimensions. Let's think about this matrix and consider what it would look like if we had only one dimension, the x dimension. The only value inside the matrix that has only x subscripts is the top left. So the matrix would consist of only that term, and the matrix would now look like it does in red. If we consider this tensor in 2 dimensions now and include the y dimension, we see that the neighboring values contain only x and y subscripts. So our new 2-dimensional inertia tensor would look like this in red. When we go to 3 dimensions, we get the full matrix back in yellow. Note that every time we added a dimension, we had to grow in 2 directions, along both arrows to represent the tensor. This is because it is a rank 2 tensor. Now, let's put our focus back to rank 1 tensors, or vectors. Vectors have only 2 important parameters or values that we assign to them: magnitude and direction. Here, we have 2 vectors which are usually represented with arrows indicating their direction. Vector A on the left is pointing in a different direction than vector B on the right, and it is clear that they have different magnitudes, or sizes. Note that vectors only have these 2 values, magnitude and direction. Vectors are not defined by where they start or end, meaning we could make vector B longer and rotate it to match the direction of vector A. And even if they are separated in space, meaning they don't overlap, they are still considered to be the exact same vector. Thanks for watching and learning about vectors. If you found this useful or want to see a specific topic covered, post a comment below or head over to my Facebook page in the video description.